inviting me to do this. It's been fun and collaborating on getting some of this data out and available. Will be good. So this is actually given several times, a couple months. I'm going to focus more on methods and the data because that's sort of the focus of what NIF does. If there are any questions at any point, feel free to ask. I think Anita will interrupt me. I can't actually see any questions. Well, actually, hopefully bubbles will pop up, but I'm happy to take questions throughout. So this is, as you all know, a brain, right? It's hopefully something we all have. And until recently, we were kind of stuck with observing it from the outside and seeing, what the brain produces. But with the advent of machines like this one, which many of you will have seen before, an fMRI scanner, we can actually now peer inside the brain and see what it's doing, without actually having to drill holes in anyone's skull, which is a nice thing. And we can generate all sorts of images, like, and these are just sort of randomly pulled from the literature, just showing you interesting things about what the brain is doing, how different regions talk to each other, what regions are when people do tasks. And so we have this really enormous literature that's developed over the last years of functional neuroimaging, and it's taught us all sorts of amazing things about the mind. At the same time, of course, there are, as always, with any kind of scientific, there are some challenges that we've had to face up to, and I'll just kind of go briefly through some of them. I might actually run through these fairly fast, so I apologize if something's not all that clear, but I kind of want to get to the methods. So things like low statistical power, or high false positive rates, lack of specificity, and information overload, really. So I'll just walk through these individually. So power, as many of you probably know, is just the probability of finding the needle in the haystack when it's, meaning if there is an effect and it's about as big as you think it is, what are the odds of detecting it? And there's a really large literature over the last 50 years showing that power is generally low in psychology studies, actually in most of the social sciences, but generally we tend to think of like 80% power as a sort of conventional, 4 times out of 5 you'll pick. It's there, actually lower most of the time. And in studies, it's actually really quite terrible, at least for one type of analysis people do, which are sort of massive whole brain analyses. Kind of give you these are some commentary on the voodoo correlations paper that Ed Vole and colleagues wrote a while back, kind of plotting power for several different kinds of tests, and I'll just kind of emphasize a couple here. So these are the power curves for a correlation. So a correlation at threshold at p equals 0.001, which is sort of the modal threshold. And what you can see, say you're trying to detect a effect of 0.3, which is a sizable correlation. Well, if you have 100 subjects, which was kind of out of the reach of most fMRI studies, you still only have about 40% power to detect that effect, right? More commonly, you're in the neighborhood of like 20, which is this blue line, and you can see that you have like 50% power, meaning the entire brain could be correlated 0.3 with manipulation you're inducing, and you're still only actually going to detect it on average in about 2% of voxels. So that's kind of several. So what this really means is that not only are you by hypothesis all of these voxels, but we're also matching the voxels significant. So we end up, look, there's just a few regions and they're correlated, when in fact it's a weaker, more diffuse correlation. Some meta-analyses that really probably about 15% of the activations that are reported in the literature are false. Now that's just taking the kind of the states. So if I ask a question, what does this brain region do? Probably many of you have answers, like the right anterior insula. And depending on where you look in literature, you might say, well, it's involved in interoceptive processing, it's involved in pain, it's involved in emotion, it's in all kinds of things. Sustained attention, arousal. And so the problem is, it can't be doing all of these things. If it's doing all of these things, then it's probably doing something actually broader than any of those. And in fact, here's a really nice image from a paper by Steve Nelson and colleagues, where they took the entire SUMS-DB, David Van Essen's group, and just plotted where the activations fall out. And you can see that, the anterior insula is a hotspot, meaning, a very large proportion actually end up reporting. So it's really unlikely that the anterior insula is doing something, really specific. Active in so many studies some pretty general. But that gets lost if you're only looking at one study, and you did a study of awareness and found the insula, so you interpret it in that context. But of course, picture of the literature. So this is to interpret activity in context, right? If you know that you induce pain, so this is my hand, nobody else was hurt in producing these slides. The state is, and then you get the image. Well, it's easy to say, oh, sure, that makes sense. It's the that fits with what we know. But imagine that your RA scrambled your images and came to you and said, oh, look, I have this image. I don't know what happened. I don't know what study it's from anymore. Can you help me? Well, now it's not so easy, right? Is that a working memory study? Is it an emotion study? Is it pain? It becomes much more difficult when you don't have that context to rely on. So establishing these kinds of specific mappings, which we'd like to do, is actually quite difficult. And kind of the last kind of point I'll make, just in terms of limitations, is just information overloads. So if you look at the number of studies that have been produced, and this is not cumulative, this is the number of studies produced every year, it's increasing, right, over time. And so, in 1993, there were very few fMRI studies, not surprisingly. But by 2009, there's 2,000 or more a year coming out. And this has consequences, right? So, there are subjective consequences to having to deal with an increasingly large literature. And, used to be you could actually follow the literature. Now you probably can't do that anymore. I certainly have kind of stop really, reading in detail almost everything, because otherwise you do nothing else. You just kind of skim, read abstracts, and then really kind of pick and choose. If we want to kind of have a sense of what doing and how it relates to cognition, of course, we need to be able to synthesize these enormous literatures, conclusions from them. So how do we kind of these issues? So one problem is, or one kind of very common approach. Well, I should say there's many different ways to address these problems. Right? You can use larger samples, which is expensive. Multivariate analysis, I think, sort of kind of a really hot area now, and I think that's really actually a good way to go. Not to actually do univariate whole brain analyses quite as often, and kind of rely on kind of data reduction and modeling techniques that can reduce the number of variables we have. But one of the best, really, still, and definitely the cheapest approaches is to use meta-analysis. And so meta-analysis is, as you probably know, just all it really is taking results from many studies and generating a consensus estimate. So it's an analysis of analyses, and these have been done for many years in psychology and other disciplines, and increasingly in the neuroimaging world as well. And the basic recipe is as follows: you take a database, which you could put together yourself, or perhaps rely on a centralized database like BrainMap, which has about 80,000 activations from 2,000 or more studies, and then you have some meta-analysis software. There's different packages, MKDA, ALE, and so on, and you do some magic. And so this is very scalable, obviously, and I'm not going to get into the details, but basically, you have all these scattered activations that look random, and then you kind of you look for consistency statistically, and you kind of can produce images that are looking. So here's just one example from a paper of Torvager's looking at emotion. So you have these almost 200 studies of emotion that individually, again, are pretty noisy. And if you were just to plot them all in the brain, they might look kind of like this, the top row here, right? So this is kind of hard to read off. You look at this and you say, well, maybe there's something, but it's very hard to determine what the structure there is. But what you do is you essentially treat each of these kind of studies as an individual data point, right? So each study is its own map. You kind of identify the regions where the largest proportion of studies activate, and you can correct for multiple comparisons in various ways. So here by doing permutation testing, And then you end up with a consensus map that kind of gives you a sense of, well, these are sort of the most reliably associated regions with the thing you care about, emotion. And so the bottom row here looks much more sensible, and it's a nice way to distill this literature down. So works really well. It's a fantastic approach. What's the problem? Well, it doesn't really scale that well because it's very effort intensive, right? If you're doing this manually, you sit there, you have to code all the studies, you have to enter them, and this can take a long time. And just to kind of give you a sense of this, so if you look at the growth of the primary literature, which is kind of this line here, this is PubMed, the number of studies over time from a nice paper by Durfus and Marr. And below that is the growth of the databases that are out there, so BrainMap, SumsDB, and so on. And you can see they're definitely growing. They're growing pretty fast, but the slope is really much smaller than the primary literature, which is to say, as time goes on, they represent a smaller and smaller chunk of the literature as a whole. Problem, because it means it becomes harder and harder to synthesize literature without spending more and more time. So the way to kind of address this really is through automation. I mean, it's impractical, right? We're not going to be able to hire, an increasingly large number of people to sit there and do this, although there are potentially crowdsourcing approaches that might work. But really, we kind of would like to automate as much of this as possible. We want to can really automatically synthesize the results from hundreds, if not thousands, of studies. And so right away, when you kind of think about doing this, there are sort of at least two big problems that come up. One is the standardization. So everyone doing fMRI uses different pre-processing streams. They are different stereotactic spaces, right? Brains are in different registers. They do completely different statistical analyses. They have very different reporting practices, and so on and so forth. And really, it's very difficult to take two papers at random and kind of make them commensurable. I mean, there's just so much variability in the kind of processing that goes on. So that's one problem. And the other is the problem of segmentation. Really, it's kind of the problem of ontology, right? So how do you automatically identify all the activations, contrasts, and studies that are relevant to X, where X is whatever you care about? It could be anything. So you care about working memory studies. Well, there's this massive literature. How do you pull out only the working memory studies and only the activation you care about to working memory, and kind of code that in a machine readable way? Like humans can do it, but machines don't do it so well. So these are sort of two big problems. So what do we do about that? So our crude solution here is, number one, for data standardization to actually completely ignore the problem, basically. Maybe not completely, but close to it. And so, as we're kind of just saying, well, let's pretend that actually we don't have to worry about all this stuff, right? We know we do, but we're going to pretend we don't, and we'll just see how far we can get. And I'll come back to this, but that's really the strategy here. And with respect to some semantic annotation, we're almost entirely ignoring the problem, right? We're not completely ignoring it, but we're just saying, let's use a really, really simple-minded approach and pretend, as I'll show you, that we can exactly what a study is about just by looking at the words that are used. So we're going to treat word use as a crude proxy for meaning. And I know that really everything I'm going to show you is really based on sort of very simple-minded approach. There's nothing at all sophisticated about the methods, which is why I'm actually a little bit surprised that any of this really works, to be perfectly honest. But it does seem to work, which is nice. But everything I'm showing you is really kind of a starting point, and there's a long, long way to go before I think it becomes as we'd like it to be. That said, of course, when we talk about people reporting activation, it's not, I shouldn't say that there's no standardization, because of course there is some sort of standard that people tend to adhere to. No matter what kind of atlas you use, you tend to report activity in the brain using the same XYZ coordinates, right? If nothing else. So you have this three-dimensional volume that we can refer to, even though it's not exactly the same volume across studies. And typically when people report coordinates in tables, there's also some standard there, right? Almost everyone will report these XYZ coordinates that you can detect. Everything else might change. We don't know necessarily what these rows mean from study to study, but at the very least, there's generally XYZ information. And if there's not that, then we really have a problem. But this really is sort of pretty almost universal. So that's something we can kind of hang our hat on. And of course, with respect to the other assumption, well, on some level, obviously, it's true that the words you use mean something, right? It tells you what the article says. So here's just a selected article from the literature. It's about narrative comprehension and memory, and the fact that those words occur a lot in the abstract in the text is indicative of what the article is about. So it's not ideal, of course, but just as a first pass, we can just count up the terms that are used and say, well, that's something, right? That tells us a little bit about what's going on. So here's a kind of schematic overview, and then I'll kind of get into the details. And all of this stuff is in our paper, which was published in Nature Methods a couple months ago. And this figure is just pulled from there. And this is kind of conceptually how it works, although say that, as you'll see, that's not exactly how it works. But conceptually, what happens is this. Let's say you're interested in pain because you're that kind of person. You like pain. You want to do a meta-analysis of pain. So you can think of this as a literature search. You're taking that term and you're just kind of asking, well, what are all the studies that use pain at a high frequency? So you grab those studies, and then you kind of scan through them, and you kind of automatically extract all the coordinates that you see anywhere in those studies, right? And you stick them in a spreadsheet or a database or something. So you have this giant list of all these coordinates that you've got from these studies. And now at that point, you can really kind of apply any kind of meta-analysis process or software package that's out there. And you can generate, all sorts of different images, and I'll talk a little about that later. But that's sort of a very, very schematic overview of how this works. And so really, there's not a whole lot to it, but the devil is in the details. Right? And so here's how it works at a slightly more detailed level. So the first thing we have to do is kind of scrape the text. And so normally when I give this talk, I skip all this stuff, but I'm going to go through it today, and hopefully you won't fall asleep. So the first thing we do is download the full text HTML for my articles from several major publishers, and the ones that I currently have covered are Science Direct, Highwire, Wiley. I think there's one or two other ones. And this actually gets pretty good coverage of the literature. So I estimate it's about 60 to 75% of the fMRI literature that's out there. So it's good. It's not comprehensive, and there's no question there are some notable omissions just because of the amount of time it takes to kind of write for every additional publisher or journal. So JCognition, Journal of Cognitive Neuroscience, is not represented, and that's a pretty high volume journal. And the reason that I haven't gone around that is because it's the only that has many fMRI articles, and so it's kind of like writing, on a case-by-case basis. And like I said, it takes a lot of time, but we like to get there eventually. A big limitation is because HTML has markup, we can use, we can tell where tables start, we can identify columns and rows, that kind of thing. It's easy to use HTML. It's not really easy to use PDFs, which don't really have much structure to them. So for now, at least, we kind of have to ignore the 20% of the literature that's still locked up, mostly older studies, in PDF format. So that's unfortunate. And of course, the parser then breaks every time that the publisher changes the HTML, which happens surprisingly often. So ideally, I think probably a lot of people would agree. I mean, we really like to move to kind of a place where the publishers all are behind some standard, and everything gets you can download it all in some format like XML or something, and we don't have this problem anymore. But for now, it's an issue, and so it's incredibly frustrating, and it slows us down. So it's not really updated in real time. Kind of every 6 months or so, I sit down for a few days and kind of update the database. The code for this is available online. I wouldn't recommend going anywhere near it. It's not very good code. I will be ashamed if you actually try to do something with this, but it is on GitHub if you must subject yourself to it. So for what that's worth. So that's kind of one side of it, is just kind of grabbing the text. And then once we have that, of course, then we need to run through and figure out what the studies are about and kind of tag each study. So as I mentioned, there's no real ontology or any kind of semantic layer here at all. It's really a very simple approach, right? We're relying on sort of any kind of structure at all about what kind of concepts are important or not important. And I'm not saying this is a good thing. I think it's a bad thing, but it's just kind of a practical thing, right? I mean, if we had to worry about the ontology, it would take us a long time before we actually got to the data. And so we decided to just plow ahead and see how it works. So it's a bag of words approach. All we're doing is we're just taking each article, taking the full text, and tagging the article with all the terms that occur at particularly high frequency. Frequency can mean anything, so we operationally would define it here as 1 token per 1,000 words. So if you have a 5,000 word article, the word language occurs 5 or more times, we say that's an article about language. If it doesn't occur 5 times, it's not an article about language. So it's binary cutoff. And it's kind of arbitrary, but it turns out the exact threshold really has on the results, which is nice. Within a pretty large range, doesn't really matter what you. We've tried other approaches, treating frequency as a continuous variable, well, for reasons I can get into later. Doesn't really matter very much. But really, that's all it is. So every study in the database now is being tagged with, you know, the words that are at relatively high frequency. Okay. We have at this point we have this full of articles, and each article terms that go along with it. Now we want to kind of pull out the coordinates so we can kind of match those up. And so how do we identify the coordinates? You know, we the fact that almost all tables have these kind of X, Y, Z. And really, it's just a bunch of imperfect heuristics. I wish I could tell you that there's some clever AI module that you know is smart, but it's not really. It's just using rules like if you find three numbers separated by commas, that's probably you know, coordinates. If you have a column called, you know, millimeters cubed, or you know, or size or extent, that's the size of the cluster, that kind of thing. And it will fail, right? But the general idea is, you know, if it looks like a duck, you know, you assume it's a duck. There's a caveat, which is that it must look like a duck in a table. So right now, we only grab coordinates that show up in tables, which means no supplemental materials, which is a but those are PDFs usually. That's the issue. And also, we don't look in the main text in the body of the article. Right? So there are limitations. But by and large, this works really quite well, and we've done a bunch of validation. There are some there's not very many. There are some false negatives, more, but still not that many. So it works reasonably well. So, of course, one thing you might kind of be wondering is, well, what do you do about the fact that there are different their data. So you can Talarak and then different MNI spaces, so it gets kind of messy. So what we have is we have kind of a preliminary algorithm that goes through and, based on the text used in the article, tries to figure out, you know, what space it's in, and then we apply a transform by produced by the brain map group, Lancaster 2007. We take the MNI coordinates.
Yep, you're still alive. I can hear. In terms of your alpha and beta errors, I've just enabled the speaker rights for all of the participants as we, if anyone has any questions. But let me just start off by, trying to probe a little more about the overlap. You say that the overlap is pretty good between the MNI and the Talarat coordinates. What way do you actually use to measure that? Can you go into that a little bit, or are you going to go into that a little bit? Mhm. Right. I think we should probably continue because I know that the participants have a little bit of a hard time flipping back and forth. So, and then I'll promote everybody. Yeah.
right? And it's easy to lose sight of this. There are all these limitations, and so I'll talk about these limitations and why there are some things that probably shouldn't use this data for yet. So words aren't states. If we come back to this assumption, clearly when you say that the study or language at high frequency, it doesn't mean it's really a study about language. There's other reasons why you might use that term, and of course, it's also a problem in the sense that a study can use lots of words. Frequency, emotion study might use the words disgust, fear, sadness. Is it really necessarily? Related to that, actually is the single biggest problem by far. There's no coding of contrast. So you might, going through this, wondering, well, how do you know what exactly an activation reflects? It's great that it comes from a study of language. Study will report several contrasts. Is it language versus rest? Is it high load versus low load? Is it one emotion versus another? What's the direction of the contrast? None of that is actually registered anywhere right now because it's hard to extract automatically. Sometimes it's easy, but most of the time it's not actually that straightforward. And so really all we know at this point is we know that these are some kind of activation that the study. We can't actually what like brain map can tell you, which is this was this experiment and this contrast and this direction of contrast. So that's a huge the specificity of the data. And similarly, we don't track activation versus deactivations. That's not as much of a problem because people overwhelm to report activations, but there's certainly some topics, some terms, this is more of an issue. I mentioned we're mostly ignoring stereotactic space differences. This is a general problem for the field. It's not like this is a unique problem for this kind of approach. It's the same for brain map or SumsDB. I mean, you can convert things, but it's never perfect. And then there's lots and lots of different spaces. So we do something about that, but not as much as like. And makes errors. So we validated this SumsDB, and I estimate the false positive about 3 to 5%. The false negative rate is probably about 15%. So it makes mistakes, but not that many. Unfortunately, that can change as soon as the publisher tweaks their HTML. This is something kind of we have to stay on top of. The kind of important point about all this is that for the most part, these limitations are going to introduce random error. They're not going to introduce systematic bias. There certainly could be some places where there could be systematic biases that are more subtle. By and large, to the extent that just kind of possible to get anything out of this. So it's an improvable question, really, like how well does this work compared to sort of gold standard approach. So in the remaining, I'll kind of show you some of the results and applications and kind of what you can do with some of this data. So the first kind of obvious question, I think, is if an automated approach works, then we should be able to do a couple things. Number one, we should be able to recapture conventional anatomical boundaries, which is to say, this approach should be able to tell you where the amygdala is, right? But certainly a human being would be able to tell where the amygdala is, and presumably people reporting on the amygdala activation of the amygdala are going to use the word amygdala to describe that. And so that's kind of a good sanity check, is that we can recapture reasonably well the conventional anatomical boundaries, like amygdala, hippocampus, and maybe more importantly, of course, really the center test is, can you produce results in a meta-analysis that are similar to what you would get in a much more careful approach. So here's kind of a comparison between anatomically defined regions. These come straight out of the Harvard-Oxford Anatomical Atlas that's shipped with FSL. And what we get using this kind of lexical meta-analysis approach, meaning we just kind of ask, okay, give us all the studies that use the term amygdala at high frequency, and then meta-analyze that. And you can see it's not perfect correspondence by any means, but it really is quite good. I mean, so like here's the amygdala, right? And so you go back and forth, you see it's pretty close. And the same is true for most of the regions. And of course, keep in mind that, to the degree there's error, part of that is because people don't actually use the terms the way they are used in the anatomical atlas, right? So, lingual gyrus, well, it's not really that clean an overlap, but that's probably because people are not all that clear on what the lingual gyrus is. I certainly am not. So that's kind of a limitation too. But it's pretty good overall. And then kind of more importantly, I think this is really sort of the gold standard test is how does this compare to a meta-analysis? And so what we did here is we took all this in our NeuroSynth database that were kind of automatically extracted and manually validated them. This was the entire lab pretty much contributed to this. And I don't think anyone was very happy to do a lot of work, which is why we'd like to be able to stop doing it manually if possible. But we got a clean data set. I think it went from about 260 studies to about 60. To say only about a quarter of those studies that the automated meta-analysis decided were really about pain and relevant to the basic pain contrast versus baseline. Only about a quarter actually ended up being verified manually. Something to keep in mind, but the kind of the interesting thing is it doesn't really make much of a difference. So the blue is the manual, and you can see it's a little more sensitive, which is good, right? It's good to know that there is some benefit to spending all that time. But really, if you're faced with, if you gave me a choice to do it over and spend hundreds of hours coding these studies versus getting like a rough past estimate, I'd prefer the latter. I mean, this is really close. Now, I should say there's no question this only is going to work this well for very broad, right? Things like pain, emotion, language, working memory. If you wanted to know, what are the neural correlates of like thermal pain versus mechanical pain, I would not suggest you use this kind of approach because that's kind of too nuanced and it involves kind of contrasts that really would need to be coded on a study-by-study level. But at least for these kind of broad domains, which are still, I think, quite interesting, we can generate these images that really, as far as I can tell, look essentially the same as what people have published in much more careful manual analyses. So that's good. That's a nice check to make sure this is basically working. Right. So then, becomes, well, what can we use this data for and these tools in terms of generating new information? So one kind of obvious application is just, you can identify the neural correlates of various states and tasks. If you can code it with words, you can kind of meta-analyze it this way. So, I mean, here's just a sample of 25 terms, and they're automatically generated in meta-analysis images. And again, a lot of these look pretty much like what people have published. For some of them, there haven't been published meta-analyses, but I would like to believe that this probably is, pretty close to what you would get. Again, these are all very general terms. I'm not saying that you can use this this is not a substitute for careful meta-analyses, unless you really just wanted, a meta-analysis of like working memory. And then I think, this is probably reasonable. And so if here we're asking, given that we know what task or what state people are in, what should we expect activity? Now we're saying if we see activity in this region, what does that mean, right? And you can see that it actually looks quite different. For working memory, it's not that much of a difference. But for emotion, for instance, you can see that all the lateral frontal stuff over here just kind of disappears. And in fact, if anything, it's sort of negatively associated, right? So this is kind of a counterintuitive point, but way to think about it is, if someone asks you, hey, I'm doing an emotion study, where should I expect to see activity? You might say, well, frontal cortex, right? Lateral frontal cortex should be in those regions, which is reasonable. But if someone says, hey, look, I ran a study, I don't know what it's of, and I got lateral frontal activity, what is this a study of? We probably should not say emotion, right? That should actually be sort of evidence against it being a study involving emotion, which is counterintuitive, but really gets at the kind of the problem of reverse inferences, right? Is that unless you have this kind of comprehensive assessment of the literature, you don't necessarily know exactly what the that kind of diagnostic sensitivity of that activation is, and so you can get really the situation where you get different. Is there a question or? Oh, okay. I just got an echo.
We're starting to run low on time, so I'm going to either have you speed this up or start to open this up for questions.
Okay. Yeah, let me just speed it up then.
Okay.
Yeah, I'll just give me like 2 minutes and then stop. Or the other thing I could do is I could kind of walk through the website, although I mean that's out there, so I don't know. What do you think?
I think you could just give us a nice wrap up in the next couple of minutes.
Okay. All right. So the reason that you get this discrepancy is, as I mentioned, because some regions are more active than others, right? So that's something we need to worry about. Skip that. The other kind of thing that you can do, or one other application, is you can actually now start to decode cognitive states from brain activity in a very general way, and again with limited specificity. But because we have lots of maps for lots of states, we can ask in an open-ended way, what does this pattern of activity imply? And so just to kind of give you a quick sense, what we can do is we can take all the studies in the database and kind of ask, given any kind of pair of terms, right? So all the studies of like, episodic retrieval versus, emotion, how well can you discriminate based on, the classifier we're training, which is essentially just the meta-analysis image. And we can do really quite well. So we're above chance. This is just kind of pairwise accuracy. We can do above chance pretty much everywhere except where we shouldn't be able to, right? So like verbal versus that's not executive, right? So verbal, well, that's actually probably one of the few cases where that's not a good sign, right? But like you look at like working memory and executive, can't really discriminate them. Probably shouldn't be able to. They're close to synonymous. So we can do reasonably well. Again, the data are noisy. We're not going to get 95% accuracy, but we can kind of decode to some extent. And I think more kind of interesting is the fact that we can also take individual subjects and do the same thing. So we can now actually take subjects from working memory studies, emotion, and pain, and ask on a subject-by-subject basis, what type of study do these subjects come from? And we can do that reasonably well, turns out, substantially above chance, about 80% accurate. Again, based purely on the literature, right? So there's no fMRI, no raw data going into these classifiers at any point, but nonetheless, based on the literature, we can actually decode states in new subjects, which is, I think, kind of exciting. I'll skip this. We can do meta-analytic connectivity modeling, kind of like the brain map has been doing, which is just saying, given a particular seat in the brain, what other regions tend to be reported together in studies. All of those maps are also on the website. And this kind of goes without saying for this audience, I think, but the kind of really the goal of this is to make all this data free, right? All the tools, the data results. Not all of them are available online right now, but they hopefully soon will be. The website feature set is limited, but it'll keep expanding as time and resources allow. So I've kind of talked about applications already. Happy to talk more. Only the last thing I'll say is just talk about some future directions, because there's kind of a lot I want to do with this in limited time. So we do want to be able to code individual activations, not studies. That's, I mentioned, the biggest limitation. There are better ways to model the text. Actually, on the website, there's some topic modeling maps that Russ Poldrak's group generated. We have some tools that are not on the website yet for conducting more sophisticated analyses. I won't get into that. And we'd like to improve the meta-analysis procedures we're using too, and there's some work there that we're trying to adapt, but this is probably a little ways off. So there's a lot to do, and it's going to continue to develop over the next 3 or 4 years. But I think, as it stands right now, the data are available and useful, and I'd love for people to use them and do stuff with them. So I'll just thank all my collaborators and lots of people who provided data, feedback, help, and happy to take questions.
Okay, thank you so much, Tal. I'm sorry to rush you along at the end there, but apparently you're getting applause from Mike. Is there, can everyone actually turn their and also Arnaud? And Jesse, excellent. So thank you all. Is anyone able to turn on their microphone so that maybe you could stop sharing so that everyone can go back to being able to see? Oh, I hear. Nope, I think it's just an echo. So does anyone need, wish to ask questions at this point?
Hi, this is Marianne. I apologize. I'm echoing that I had technical difficulties, and so I may have missed something. But one of the things that we're very concerned about it is how we can promote better practices in the scientific, the neuroscience community, to make it easier for us to be able to extract these things from literature. Can you conceive that there would be a format for publishing coordinates or something that would make it faster?
Yeah, absolutely. So I think there's one is the question of the format, but just being able to get a. One issue is, like I said, some of the publishers, surprisingly, open access publishers like Frontiers, doesn't, they don't have tables. They have images, right? So the tables are images, which is not really helpful because you can't get at the data. So that's kind of an issue. I think definitely all the publishers should be using, at least an HTML version should just make the data available directly. Beyond that, I think there's not much that, again, it's a question of kind of how much specificity you want. As a first pass, I would love it if just, there was some standard format for reporting just tables in XML, and even if it was just XYZ coordinates, right? So part of it is, of course, making authors do the work, but if nothing else, I think it would be easy for everyone to label columns XYZ, and and then of course we can talk about other stuff that would be standardized, like statistical effect size measures, statistics, and so on. But I don't think I think settling on a standard is not going to be that difficult. I think getting the publishers to adopt it and then getting authors to buy in, those are it's really the social engineering problems that I think are going to be more an issue. And I don't really have a great sense of how to go about that, but I think almost any kind of standard will suffice. It'll be easy to pull the data we need for this, at least. I think other kind of issues, like once you get into ontologies, then I think it's a much bigger deal. But for the kind of stuff that I've been working with in these data, I think almost anything would do, as long as there was kind of a consensus.
Thank you. We've had a re-unmuting. Any other questions? There was one question from Jonathan. Is there a better format for publishing coordinates? And I'm not sure exactly what Jonathan means by that.
Is that what we just talked about? Or is that also, I remember when we tried to develop some tools for just displaying coordinates, there were all these different correction factors and things that you needed to put in order to get things to display on a brain. And, we learned from David Van Essen that a coordinate was not just a coordinate. And it wasn't just that you had to pick Talarak and MNI, it was you had to pick some flavor of it, you had to have the decimal points, there was all kinds of stuff you had to do.
Yeah, absolutely. I think this is kind of another, again, it's like, it comes back to this question of you have a choice at this point, right? You can either have the really kind of carefully curated data, and then you're restricted to much less of it, or you can kind of, you can go with lots and lots of data that's not very good. So
Right.
yeah, I think it's going to be hard, at least in the kind of the near future, to get a standard that takes into account all that stuff, like you're saying. And I've talked to David about this too. And I mean, yeah, a coordinate's not a coordinate, but all the stuff that would really go into figuring out what it is and being able to convert it into a standard format, that's a really hard problem. And at some point, I think you do get into diminishing returns because, so yes, there are different SPM M&I spaces, but are the differences big enough that we should worry about, I'm not sure, right? Whereas, M&I versus Talerac, I think is kind of a big difference. And so I think
Mm-hmm.
we should be kind of pragmatic and kind of figure out what the kind of minimum that works is, and then kind of slowly try to do more as time goes on.
Yeah, that's our opinion, is that there has to be some minimal things, and it involves a whole bunch, again, the cultural practices for recognizing that when you publish your lovely paper on coordinates, that there's going to be something else that wants to consume those coordinates and use it for something else. So that some attention should be paid to that if we know what to do. We may not know what to do because there may not be a standard practice, but this is one of the things that NIF has found. This practice of publishing tables as figures is ridiculous. I mean, that presumably could easily be changed by everybody, or at least, even if you do publish it as a figure, if you do some sort of, at least if it's in a standard format, we might be able to extract it. But yeah, I do think that we have to start educating the community about publishing, because what I'd like to go after is the neuroscientist says, listen, if you just tell me what to do, I'll do it. Can't be overly burdensome, but a lot of what we are asking for is not overly burdensome. It's just practice.
I will say, just as a quick follow-up to that, an alternative approach that I really kind of like is to incentivize people to give us their maps, right? So, the coordinates are good, but of course what we really want is the actual statistical map that got distilled down to that. And so one of the ideas here is, what incentive do people have to share those images? Well, right now, not a lot, but given an interface like NeuroSynth, and hopefully, like a third party would come up with a better one, because this one's pretty rudimentary. The idea is just, so you run your analysis, you upload your image, you get a unique URL, now you can stick that into your paper. And so people don't have to worry so much about, the where is that, and look at the XYZ coordinates. They can actually go get the data. And that would be fantastic from an analysis standpoint. And it would really kind of circumvent, in some ways, the publisher and, those kinds of issues. And I think that might not actually be so hard to do, to get authors to do that, right? If you can actually visualize your image and other people can see it. I think most people do that. So that's, I think, something to push for as well.
Yeah, especially if your reviewers start to insist on it. And I think that is starting to happen. I'm starting to see in reviews of grants and reviews of papers, it's like, you're not making your data available, and you should go and do this. So certainly anything we can do to help push that along, we'd be happy to help.
Okay, well, I think our time is more or less expired. Fahim had raised his hand. Excuse me. Fahim had raised his hand. Can you unmute yourself? Is there one final question from Fahim? Okay, I guess he's either unable to make his microphone work, or has withdrawn his question. Alrighty, well, thank you very much, Tal, and thank you everyone for participating. Our time has expired, and we will see you again at the next webinar. Thank you very much. And there seems to be, again, some applause from the crowd.
The last thing I'll say is, I'm happy to answer any emails or give people whatever data they want. So feel free to email me.